right? So we know something about all these powerful tools that have been developed, quantum mechanics around 1925, 26 actually, and then all these much more modern things, including scanning probe microscopy, which is really quite recent. But the most powerful tool in organic chemistry for everyday practice, and certainly for anybody who's not a professional chemist and into the quantum mechanics and stuff like that, is bonds. This amazing invention of bonds and how people knew what things were like before any of these tools were dreamt of, right? And for that, we go back in time and look at these guys in the 19th century who invented it. And we begin with what's called, we begin with, sorry, here we go again. Okay, we begin with the chemical revolution, right? That's a name that historians of science have given this period, beginning with Lavoisier. So really that's where we'll start. But he didn't just spring from nowhere. There was a long tradition of some kinds of chemistry before that, and we're going to just review that very briefly. There's a background in ancient art and lore. Okay? So for example, here's a mosaic from Monreale in Sicily of Noah, right, as making wine and then falling victim to it and having his shame hidden by his sons, okay? And here's his flask, right? So this is like, 3,000 years ago. The mosaic is about 1,000 years. That's 12th century. It's 900 years old. Okay, here is a Roman glass perfume vial. It's 2,000 years old. So they made perfume, obviously, and extracted the stuff from flowers and whatever that would do that. Okay, there's the chemical research building when it was 5 days old. Okay, and we already saw Francis Bacon, who said all the philosophy of nature which is now received is either the philosophy of the Grecians or that of the alchemists. So the alchemists are, in a sense, our ancestors. He didn't have a very high opinion of them. He said, the one is gathered out of a few vulgar observation, that's the Greek philosophers, and the other out of a few experiments of a furnace, right? The one never faileth to multiply words, and the other ever faileth to multiply gold. So even at this time when science was beginning to get underway, modern science, alchemy was already in disrepute, but it did contribute some things. It didn't contribute much to theory, because the theory depended on Greek, on the Greek antecedents and the authority rather than observation. But they did fiddle around. Here's a painting of an alchemist from 1663. And remember, Newton did more work in alchemy than he did in physics, right? And he wrote an enormous amount but never published anything about it. There's a great website now from the University of Indiana of all Newton's alchemical works, and you can look at them. But this was to be kept a secret. That was the idea of alchemy, right? That it was occult, it was hidden, okay? And in fact, there's a show that's coming up on alchemy at the Beinecke Library in January of their holdings in alchemy, and the title of the show is The Book of Secrets, right? And that's Harry Potter as well, right? Okay. So here's one of the things that's going to be shown. It's part of a really long scroll, which is the Visio Mystica of Arnold of Villanova, who was a 13th century alchemist who was into medicine, was considered the greatest medical authority of its time. This particular scroll was written in England in 1570, so a lot of it's in English. It says the Red Sea, the red loon, the red moon, the red soul, the red sun, right? All sorts of mystical things. And then, and you see here is the corpus, the body, which is earth, and here's the soul, which is oil, and here's the spirit or the air, the breath, which is water. So everything was a symbol for something else. Or if you look at the four corners of this, on the bottom right, we have air, right? Air, it says, is hot and moist, right? Or in the top left is earth, which is cold and dry, the opposite of air. And down here is fire, which is hot and dry. And up there is water, which is cold and moist, right? So this was supposed to be something profound and mysterious. Another thing they're going to show is this book on the Philosopher's Stone, which was written in the 13th century. The particular copy they have is from 1571. But it looks like somebody's organic chemistry text after they've highlighted it in preparation for the exam. Every word is underlined, right? And all in the margin are these fingers pointing to important things, right? And if you look there, you'll see great words like, you know, alchemy there. You see elixir. I forget, there are a lot of key words, but fundamentally it's all nonsense, all the theory. The reason people kept it secret really was, I think, not to keep other people from finding it out, but to hide the fact that it was nonsense. That's just my own theory, so maybe that's wrong. Okay, but Paracelsus in the early 1500s was an alchemist, a traveling physician, and he developed what had been long before that, which was the doctrine of sympathies. And that one aspect of that was, in nature, antidotes for poisons are to be found near the source of the illness, right? So for example, you know what that is? Poison ivy, right? But near poison ivy, you're likely to find jewelweed, which is an antidote for poison ivy, right? Or that poison ivy is a New World thing, so that didn't interest the alchemist. But this one certainly did. Willow, salix is the Latin name for willow, which is found in malarial swamps. So you go into a swamp, you get malaria, but you also find the willow there. And the willow bark, extracting from the willow bark, you can get salicin, a glycoside, which is a sugar plus aromatic thing there, right? And if you hydrolyze that to get the sugar off and oxidize that to make a carboxylic acid, you get this. What's that?
Salicylic acid.
Right, salicylic acid from salix, right? So it's good for fevers and so on, for your malaria. Okay, so that's the theory. This is another thing they're going to show, a Vade Mecum, Come Along With Me, which is a lab manual that was kept by Caspar Hartung from Hof in 1557 in Austria. So you can see he draws various, he's reading various things, right, and writing extracts and notes to himself about it. It's like your pre-lab preparation, right? Okay, and you notice who he's quoting up here? Arnold, that guy from the 13th century who did the thing we've showed first, right? Arnold of Villanova. Okay, but he shows distillation apparatus. These things are called pelicans. Isn't that interesting? And here's a lamp. And here's somebody, he's filtering something through some kind of screen or grid there, okay? So they developed tools, right, that were of great use to chemistry once chemistry got going. So there was a lot of, even though the theory was nonsense, there was a lot of practical background in preparing various elixirs and so on. So this was crucial. Now here is a lab that could easily be mistaken for an alchemical laboratory, but in fact it's an early chemical laboratory, and I'll show it to you here. It's this book. It's this picture here from 1777, from a book about air and fire. And it reports the discovery of a new element in this book. And it's by Carl Wilhelm Scheele, who is in Uppsala, in Sweden. What do you think he discovered with light and fire? Or pardon, with air and fire, Luft und Feuer? Aha, we'll see. Okay. So that's his laboratory, Scheele's laboratory, or at least some artist's impression of it. And here he is, he's before the chemical revolution, but he's an important precedent, as you'll see, to the chemical revolution. He was, by practice, a pharmacist, but he spent most of his time doing what is really chemical research. Here's a picture of a stamp, a Swedish stamp, of showing Scheele, except it's not Scheele. Turns out the costume he's wearing wouldn't have been developed until 40 years after Scheele died. Okay, but he purified organic compounds that weren't easy to purify, in particular carboxylic acids. So he got an acid that he called lactic acid, which we now know has that structure. Where did he get it? From sour milk, okay? And so here's his paper about that, on milk and its acid, right, from 1780. So he purified these acids as salts that he could crystallize. That was the method of purifying. So here's several reports in that paper. Item 7, bismuth, cobalt, antimony, tin, mercury, silver, and gold were attacked by lactic acid, either by digestion, that's just sitting there under it, or by boiling. After standing over tin, the acid caused a black precipitate to form in a solution of gold in aqua regia. Right? So this is not mysterious writing, right? It's talking in language that we can understand, even though it's translated from German. Iron and zinc were dissolved with the formation of flammable air. What do you suppose? He reacted acid with zinc and he got flammable air. What do you suppose that was? Hydrogen, right? The iron solution was brown and gave no crystallization, but the zinc solution crystallized. Why was that important? Because he could purify it if it crystallized and get just that salt, right? So that's how he got pure samples of acids, right? With copper, our solution first took on a blue color, then green, finally dark blue, but did not crystallize, unfortunately. And 10, lead dissolved after several days of digestion. The solution acquired a sweet tart taste, but did not crystallize, right? So what do you do when you don't have IR and NMR, right? Sure, so he tasted all these things. Cyanide too. Okay, so he got citric acid. Where did he get that?
Orange, lemon.
From lemons, okay? And he got uric acid. Obvious. He got tartaric acid. That's a little, tartaric acid, his discovery, turns out to be one of probably the single most important, maybe the second, no, probably the most important compound in the 19th century, as you'll see. Okay, that comes from tartar, which is the deposit on the inside of wine casks after you've fermented wine. Okay, benzoic acid came from gum benzoin, a product of the Far East. Okay, and oxalic acid, where do you think that came from? It came from rhubarb. Now, why oxalic? Why oxy? Oxy means sharp. So what does sharp have to do with it, with rhubarb? Yeah, so you know oxy as a root meaning sharp. Oxymoron doesn't mean a stupid ox. What it means is sharp, and moron means dull. So it's a sharp dullness is an oxymoron. It's a self-contradictory word, right? So what's sharp about rhubarb? Its taste. It tastes acidic. In fact, the word acidic comes from the Latin acidus, which comes from acre, to be sour, which comes from, the root is oc, which means sharp. So it's the same thing, acid and oxy. Okay? So look at all these things. They have what? The carboxylate group, which makes them acidic, right? And we know why it makes it acidic. This is a review from last time, right? This functional group, it's not a carbonyl alcohol, it's a carboxylic acid. The high HOMO is stabilized in the acid, but it's even more stabilized when it's an anion because you have a higher HOMO. So it changes the acidity, the ease of dissociation of H plus, by a factor of 10 to the 11th, right? Which depends on the energy difference between those two. So if you more stabilize the anion product, then you stabilize the starting material, then you shift the reaction toward product, here by 10 to the 11th. Big change, okay? But actually there's more to it than just that resonance, just that HOMO-LUMO interaction. There's a thing called inductive effects that we'll talk about later on. But a large part of it is due to that. Okay, but you notice there's one exception here. Uric acid doesn't have a carboxylate group in it. So there's what it has. And notice that it has an unshared pair on nitrogen. Like an amide, it's stabilized by a carbonyl. In fact, it's stabilized by 2 carbonyls, 2 adjacent LUMOs to stabilize it. Now, if that were just stable, it wouldn't be a reason to get rid of it, to lose a proton. But the anion that you get if you lose the proton from nitrogen has a higher HOMO. So it's even more stabilized. The same trick as in carboxylic acid, but even more so, as you'll see here. The pKa of this compound is 5.8. It's pretty acidic, right? But a normal amine, like ammonia, losing a proton, has a pKa of 38, right? So this is 32 powers of 10 helped out, because it has such a high HOMO on the nitrogen and 2 carbonyls to stabilize it. Okay, so uric acid is indeed an acid very like carboxylic acids. Okay, now Scheele not only did these organic acids, he also discovered or co-discovered 7 elements. They're listed here according to what row of the periodic table they're in. Notice down at the bottom here you have tungsten, right? Tungsten comes from Swedish. He was Swedish. It's tungsten, heavy stone. Being way down, it's got lots of protons and neutrons and is very, very dense, right? So it's heavy. The stones that comes from it are very heavy, right? But by contrast, these up here are gases. And in fact, that's what got the 19th century chemistry going. That's what launched the chemical revolution, was the ability to work with gases. Because to be a gas, something has to be a small molecule, and therefore simple, or at least relatively simple. So you had to start with simple things before you could get to complex ones like salicylic acid in terms of understanding. Now Scheele in 1771 had heated silver carbonate, and he found that he got CO2 out. I mean, he didn't know it was CO2, but the gas came out, okay? And if you heated that still more, greater than 340 Celsius, then you get silver and oxygen comes out from silver oxide. This gas, this Feuerluft, right? Fire air. That's what the book is about, okay? So he wrote the book, but the book starts, as I'll show you here. Sorry. There we go. The book starts with an introduction, a Vorbericht, which is translated, it says, from Swedish, and let's see where it says here. And it's by Torbern Bergman, written in 1777. He had this book written for 2 years waiting for this preface to come. Bergman was a busy guy, right? And during the time that this book was sitting ready, the manuscript was sitting ready to be printed, Priestley in England discovered oxygen. So this book came out after Priestley. But there's no doubt that Scheele had discovered it earlier. His lab books from 1771 show it. And here in 1774 is his draft of a letter that he wrote to France. And it actually begins with a couple words on the previous sheet, but it says, "Since I have no large burning glass, I beg you to try with yours." Because he had to do this heating things in an oven to really high temperature, which was hard to do. But if you could do it with a focused light of the sun to heat it, then it would be much more practical. And in France, they had such a big magnifying glass, right, that would allow it to do it. But that letter, although it was sent, was never answered. And you know who it was sent to, presumably? Lavoisier, the founder of the chemical revolution, and another discoverer of oxygen. Okay. Okay, so now we're going to talk about Lavoisier, who was, wasn't a perfect person, but he was really very, very good. Okay, now the chemical revolution began, you can say it started in 1789, the chemical revolution. And that's not the only revolution that started in France in 1789, right? Do you know what this is? What? It's the tennis court oath when the legislators, so to say, gathered to say that they wouldn't disband until the king granted them certain things, and you know what that led to in 1789. The only guy that didn't agree was this guy here. He's the only one that didn't sign it. But at any rate, it was radical. Now there's an Indo-European word that's a root of many words called werad, and it gives words in all sorts of languages, like it means root, okay? And Wurzel in German means root, and wort, like St. John's wort, is a root. Licorice, glucose rhiza, Greek, the rice is root, okay? Sweet root it means, okay? Race, razza in Italian, is the root of your being, right? Rutabaga, radix in Latin. And you know lots of words come from radix, like radish is a root. Or eradicate, what does that mean? It means to pull it out by the roots, okay? Or radical, something that's radical is something that goes right to the root, back to the very origin of something. And that word used in that way, if you look in the Oxford English Dictionary, it was used coined in mathematics in the 16th century. The root of a number is its origin, right? If you take the square root of a number and multiply it by itself, you get the number. So it's the root of the number, the radical, right? Or in politics, it was used in 18th century in England, and in chemistry in 18th century in France. The idea of radical as the root of things began to be used, which we'll see. Okay, so 1787, radical was introduced as a political term according to the Oxford English Dictionary by J. Jebb, whoever he was, presumably a politician. Or in 1787, there was this radical document, We the People, right? But that same year, 1787, radical was introduced as a chemical term by Louis Bernard Guiton de Morveau. And it was in the context of developing nomenclature for chemistry. So he, together with Berthollet and Fourcroy, developed a new method for nomenclature in chemistry. And here's a book. This is not the original French, but it's the first English translation, which you see comes from the Yale University Library back when. It's from 1788. Okay, so a method of chemical nomenclature by Guiton de Morveau, Lavoisier, Berthollet, and Fourcroy. So the fourth author of this new method of chemical nomenclature is Lavoisier. So there's Lavoisier with his wife. This is part of an enormous picture that's in the Metropolitan. And it was commissioned by Lavoisier and his wife, who hired Jacques-Louis David to paint it. And they paid 7,000 pounds to the artist to paint it, which is the equivalent of $300,000 today. They were quite well-to-do. They had an income of the order of $1 million a year, or the equivalent. It depends on how you translate numbers, of course. It's hard. So here he is at the age of 45 in 1789, and he's working on drafting. So you know, these guys, when they had their portraits painted, always put something important in it. So what did he choose to have? He chose to be working on a manuscript, and the manuscript he's working on is the manuscript of this book, right, from 1789. It's called Traité élémentaire de chimie, the elementary treatise on chemistry. And the other stuff he put in the picture is the equipment. There it is the equipment he used. So here you see various equipment from one of the plates at the end of the book, and you can see these items in the picture. There's that bell jar. There's that device. There's that big 16-pint flask with a brass fitting on it. There's that valve that you attach to the bottom of the flask. And over here is a portfolio. And the portfolio says down in the corner, Paul's Lavoisier Sculpci. That means this was drawn by Paul's Lavoisier, who is his wife. She was his assistant in the laboratory, kept all the notebooks, read English for him because he couldn't read English, so he had to do anything with Priestley. She would read it to him. But she drew all these things. She studied with David drawing in order to be able to do this. Okay, she drew she painted this portrait of their family friend. Who's that? Yeah, Benjamin Franklin. I showed you that picture earlier, said we'd refer to it again. So this is that particular plate in the book, and it relates to weighing a gas. Right? It'll turn out that the most important thing for Lavoisier and for the whole 19th century, all this development that led to bonds and their arrangement, weighing was the key thing. But how do you weigh a gas? So you need gases so they're simple enough to deal with and easy to purify, right? But you need to weigh them. So how can you weigh a gas? Well, you can collect a gas, as shown in this picture, by generating it in this retort G, and it comes and it bubbles up, displacing water or mercury, most often mercury, from a bell jar. You've done this kind of thing? Some of you? But you can see how it would work. As it bubbles up, the mercury comes down, okay? So now you have the gas. Now we'll shift attention down to the bottom right here and see how this works. So we have this bell jar on the bottom, which is fitted with valves on the top, is filled with mercury, and it's in a pool of mercury. And then this big 16-pint flask is evacuated. You used one of these pumps. Remember, 100 years before this, Hooke, or 130 years before this, Hooke made a great vacuum pump for Boyle. Boyle is the only person on the front of the building older than Lavoisier, right? And that was dealing with gases and Boyle's law, how pressure and volume relate to one another. Okay, so anyhow, he could evacuate that with a pump, then seal it off, turn the valves off, and he's got mercury in that thing. And now he puts a tip underneath it and generates gas, and it bubbles up and fills this container with the gas, and it's sitting in a mercury pool so that it's not communicating with the atmosphere other than through the pressure through the mercury pool. Okay, so now he opens the valves, so the vacuum starts sucking up the mercury, that is pulling the air in, up to a certain point, right? Then the mercury stops rising, okay? And now at this point you know that the pressure of that gas is atmospheric pressure less whatever the height of the mercury column is, right? That's how a barometer works. So he knows how much gas, what volume of gas he has in A. He knows he filled it with water first and weighed it to see what its volume was. Now he knows the volume, he knows the pressure, so he knows how much gas there would be at atmospheric pressure, right? And now, of course, he just turns off these things, unscrews the thing on top and weighs it and sees how much heavier it is than it was when it was evacuated. And that's how much the air weighs, and he knows how much volume, how much pressure, so he knows how much whatever gas he collected weighed, so he could weigh a gas. Pretty clever, huh? Okay, here he is working with one of these bell jars. Now, these bell jars were filled with mercury. I don't know if you've, here, would you help me out, Wilson? Lift this up and show it to the class, but don't lift it high, hold it above the thing. Did it surprise you? Yeah. He said it surprised him. And you can come up afterwards if you want to and be surprised yourself by lifting this up. But keep it over this because people are so panicked about mercury nowadays. I heard on the way over to class while I was bringing this, I heard there's a new law in the European Union that it's going to be illegal to transport mercury over international borders. Go figure. Anyhow, there's Lavoisier doing an experiment with this big thing of mercury, right? He must have been a stout person, okay? This is him in his library with Madame Lavoisier taking his dictation as he does his experiments. Okay, so here's the Traité élémentaire de chimie, and I'll show you this actually is a facsimile, not the real thing. But here's the title page, the first volume. Okay, so you can look at that if you want to. And at the end, I'll just note here, at the end of the second volume are all these pages, which are devices, like this is the one we just looked at. Okay, so if you want to look at them, feel free. Don't handle the other one though, it's real. Okay, so Elementary Treatise of Chemistry, presented in a new order. This is the revolution, according to modern discoveries, with figures, as I just showed you. And 1789 is the date, the same as the French Revolution. Okay, you notice he's a member of all different academies, including Philadelphia. Why in the world would he have been a member of the Scientific Academy of Philadelphia? He never went there. Right, his pal. Okay, 1789. So it has the most wonderful introduction called Discours Préliminaire. And he says, my only object when I began this work, or I had no other object when I began the following work, than to extend and explain more fully the memoir which I read at the public meeting of the Academy of Science in the month of April 1787, remember when radical was introduced and so on the necessity of reforming and completing the nomenclature of chemistry. So that's all he was trying to do, was get a proper nomenclature that would be useful, in contrast to all this alchemical nonsense. Okay? While engaged in this employment, I perceived, better than I had ever done before, the justice of the following maxims of the Abbé de Condillac in his System of Logic and some other works. So this is what Condillac said. We think only through the medium of words. Languages are true analytical methods. Algebra, which is adapted to its purpose in every species of expression in the most simple, most exact, and best manner possible, is at the same time a language and an analytical method. The art of reasoning is nothing more than language well arranged. So Lavoisier goes on to say, thus, while I thought myself employed only in forming a nomenclature, and while I proposed to myself nothing more than to improve the chemical language, my work transformed itself by degrees, without my being able to prevent it, into a treatise upon the elements of chemistry. So in the process of reforming the language, he reformed the whole understanding of the science. The impossibility of separating nomenclature of a science from the science itself is owing to this, that every branch of physical science must consist of three things: the series of facts, which are the object of the science, the ideas which represent these facts, and the words by which the ideas are expressed. Like three impressions of the same seal, the word ought to produce the idea, and the idea to be a picture of the fact. So all these things have to be harmonious, right? Three impressions of the same seal. And as ideas are preserved and communicated by means of words, it necessarily follows that we cannot improve the language of any science without at the same time improving the science itself. Neither can we, on the other hand, improve a science without improving the language or nomenclature which belongs to it. However certain the facts of any science may be, however just the ideas we may have formed of these facts, we can only communicate false impressions to others while we want words by which these may be properly expressed, right? So clarity as opposed to obscurity was his goal, as opposed to Newton or the alchemists, right? Facts, ideas, and words, and they all have to tie into one another as impressions of the same seal, okay? So he presented things, as he had advertised, in a new order, very different from any book on chemistry that had been written before. First was doctrine, that is the theory, the first part of the book, which is a 2-volume book, so almost all of the first, no, about 2/3, I think, of the first volume are doctrine. And then nomenclature, that's what he had set out to do. And finally, operations, how you can actually repeat this stuff for yourself, what devices you need. Of course, he was very wealthy and could employ people to manufacture all the equipment he needed. Not everybody could do that. But he showed exactly how it was done and gave it's easy to understand exactly what he did. Now, one of the first things he turned his attention to was elements. He says, if by the name elements, we mean to designate the simple, indivisible molecules, molecule just means little thing, right, that make up substances, it is probable we do not know what they are. They're just too small, right? But if, on the contrary, we associate with the name of elements, or the principles of substances, the idea of the furthest stage to which analysis can reach, all substances that we have so far found no means to decompose are elements for us. They behave with respect to us like simple substances. So it's an operational, not a philosophical definition of element. If you can't break it apart, consider it an element until you can break it apart. We have elements here, the chemical elements. Are they elements according to Lavoisier's definition? Like here we see cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium. Are they elements according to Lavoisier? Why not? You can break them apart into nuclei and electrons. The nuclei you can break apart into protons and neutrons, and you can break these things apart into quarks and so on. But for Lavoisier, or for chemists, those are elements because you don't break them apart. Okay? So here's a table of simple substances in the first English translation of the Traité élémentaire de chimie. So here's a table of the elements. Simple substances belonging to all the kingdoms of nature, which may be considered as the elements of bodies. So what are the first two elements? Things that you can't break apart. Light and heat are the first two elements, which we don't see in Mendeleev's table, right? Because they're fundamentally different from the other elements because they don't have any weight. You can weigh a gas, but you can't weigh light, and you can't weigh heat, okay? So he gives new names to these things, light and caloric, and what the old name was. Light used to be called light too, but in his new system he's going to keep the old name. Or caloric he's going to use for what used to be called heat, or the principle or element of heat, or fire, or igneous fluid, or the matter of fire or heat. Those were terms people had used before, but he's going to call them caloric. Okay? Now, if you have caloric, you must be able to measure it. If you can't weigh it, what you can do? You can use a calorimeter to measure it. And this is the calorimeter manufactured and used by Lavoisier, and also Laplace, a younger man who was his colleague who became a great mathematician, as you probably know. So here's the thing, it's big. That's a 3-foot rule, right? So this thing stood this high off the table, right? Okay. Now here's what it is. There's a lamp that's going to make fire. There's oil in the well of the lamp. And you're going to measure how much heat you get out of burning that oil. So you put it inside this bucket, and you put the bucket in this mesh cage and put the lid on. Then you put that cage and its lid up into this can. Okay? And now you light the flame in there. You want to measure how much heat it gives. How do you measure the heat? What you do is surround it by melting ice. So the heat will melt the ice. Now there's going to be a problem. Obviously the more heat, the more ice you melt. But that's not the only place heat's coming from. Where else will it come from to melt the ice? From outside. So this is where the thing is clever. So there's another can outside that can, and you fill it with ice, which is an insulator for the inside. So no heat comes from any heat that comes from the outside melts the outside ice, not the inside ice. Only the flame will melt the inside ice. Okay, notice that the lids also are covered with ice too, so it's completely surrounded by ice and then by another layer of ice. So the flame burns, 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 and you fill water. Water comes up as they melt in both of them, and then you put that thing underneath and turn the tap, and see how much water was melted only by the flame, right? And that measures how much heat. Pretty clever, huh? Okay, so that's a fact, is measuring how much heat there is. But analysis in general is it. This is from the Oxford English Dictionary, which Yale has a subscription to, so you can look up words to your heart's content. It's a lot of fun. This year is the 80th anniversary of the Oxford English Dictionary. There was a symposium down the hill sponsored by the library, with including the guy that wrote The Professor and the Madman. Has anyone read that book about the Oxford English Dictionary? It's a wonderful short book. And the Madman was a Yale graduate. It's an interesting story. And the other guy was one who read the Oxford English Dictionary cover to cover, 20 volumes within 1 year. He wrote a book about that during the last year. It was a fun thing. But anyhow, it's fun to look up things in the Oxford English Dictionary. And here's analysis. So you see it comes from ana, and I think it's lysain, but I can get some help on that. Luane. Luane, okay, anyhow. But it means to loose, according to the Oxford English Dictionary. So it's to loose back, so to take things apart is the sense of it. And generally, it's the resolution or breaking up of anything complex into its various simple elements, so you can analyze a passage in literature, okay? It's the opposite of synthesis, okay? The exact determination of the elements or components of anything complex. Specifically in chemistry, the resolution of a chemical compound into its proximate or ultimate elements. Now, proximate and ultimate, what does that mean? You can see down in the historical uses of it what proximate and ultimate mean. 1791, this same time, 1789, remember, it's the Traité élémentaire, said the quantity of charcoal which something yields by analysis. So you find out how much charcoal is in it. That's the word we now say carbon, right? So that's elemental analysis. That's ultimate analysis. Take things all apart to the chemical elements, see how much of each one. But there's also this thing called proximate analysis, which you can see from this quote in 1831. Sugar, starch, and gum are proximate principles, and these we obtain by proximate analysis. So you can take some food stuff and see what percentage of protein, what percentage of sugar, what percentage of this, that, and the other thing. So what you read on a candy bar or something like that, that's proximate analysis, not elemental, not ultimate analysis. So both kinds are important in Lavoisier's work, as we'll see. Okay, so we looked at light and caloric. Now let's look at a few of these elements, the ultimate elements here. We have the fact, the theory, and the word for these things. So how about azote? Why is that word, that's the French name for, the French still call nitrogen azote. And in this English translation, it was called that in 1790 or 91. Okay, where does that word come from? What does the prefix A mean? Without. And how about zo? It's great we have somebody taking Greek. Without life. In what sense is that an appropriate name, a meaningful name for nitrogen? Alex? What kind of tests? Yeah, if you put a mouse in an atmosphere of nitrogen, it's azote, right? So that's what the name meant. So he used, it used to be called phlogisticated air or gas or Mephistus or the base of Mephistus, right? Azote is the name that Lavoisier decided to use for it. Or hydrogen. How about it? Help us out. Pardon me? Water. What about water? Hydro is water. What's gen? It makes water, right? So if you burn hydrogen, you generate water, right? So hydrogen, okay? How about oxygen? What does it generate? Acid, sourness. So oxygen is the element that generates sourness, that generates acid. And that is the key element in Lavoisier's theory, the oxygen theory of combustion. Okay, so oxygen plus a base or radical, right? So these two terms meant the same thing to Lavoisier, the fundamental radical, the root of some substance, right? And you react it with oxygen and it makes the stuff into an acid. Can you think of an example of an element that you react with oxygen and it becomes an acid? Well, let's just look in his table. Sulfur, you burn it and it becomes sulfuric acid or sulfurous acid, right? Phosphorus generates phosphoric acid. Carbon generates carbonic acid. Muriatic radical, which we don't know, they haven't discovered the muriatic radical yet, the base of that acid. But if you burn it and combine it with oxygen, you get muriatic acid. Does anybody know what muriatic acid is? Hydrochloric acid. How much oxygen is in it? None, right? But that was the theory, right? That you take a base, you react it with oxygen, you get an acid. So there must have been a muriatic radical, okay? Unfortunately, that part of it was wrong. The same for fluoric radical, okay? But then there were also compound radicals. Radicals that were only proximate, not ultimate, right? Radicals that had several other elements in them, right? And here were some of those, like a list of those radicals with the names that Lavoisier decided to use for them. And many of them, all the ones indicated by an arrow, are ones that Scheele had already discovered, right? Like tartaric, citric, oxalic, benzoic, lactic. Lithic acid was another one that I didn't mention before, which comes from stones. See, it's from the urinary calculus. Okay, so those were compound radicals. And that's the end of today's lecture.